sampling rate is 300 kilohertz. As a reminder, this is about 10 times better than what you will have on your audio card. So it's a pretty good analog to digital converter, and this allows me to monitor my environment. I can monitor a voltage of whatever is happening around. How do you write a piece of software for controlling this ADC? Exactly like we did before, we will address this 8 million address. We say that we are using an unsigned short. We want to read 16-bit. But this time, instead of assigning a value, we will read a value. We read the value. So this time, instead of having write signal being triggered, we have a read signal being triggered. And at this point, the ADC will provide its value. Now, there is a little trick with ADC. An ADC requires a signal to tell you, start your conversion. So with an ADC, you must first tell it, start converting, wait a little bit, that's an empty loop, and when it's finished converting, this is the time when you start reading the results. So you have to access an analog to digital converter both for a writing procedure and a reading procedure. Now, I mentioned to you, with all these examples, I use a piece of software that I'm familiar with as a Linux developer. But as I mentioned to you from the beginning, if you try to do anything but running your own little program, you will simply run out of memory. Even if you type less is more or less the easiest program I can think of under Linux, less will run out of memory. Not even mentioning graphical interfaces such as SDL or Qtopia, embedded Qt. So there is simply no way of using DS Linux as a reasonable environment on the NDS. And one way of doing this, as you would do on your PC, is simply upgrade the memory of your NDS. So you just buy another memory cartridge, put it on the slot 2 that exists, it gives you 32 megabytes, and indeed you can run the Wi-Fi, you get access to all the Wi-Fi interface configuration of Linux, but you don't have access to your slot 2 anymore. And personally, I'm not a great fan of saying, I have a piece of hardware that's not powerful enough, so I will upgrade it. I prefer thinking of downgrading my software, which is doing far too many things compared to what I need. So that's more or less the opposite of what you would do on your PC. So the opposite is, I want to find a new operating system that does the same or gives me the same feeling than Linux, or will provide the performances that I'm looking for, but with a much smaller footprint. RTEMS, the real-time, must be written something, the real-time executive multiprocessor system, I think, is an operating system originally developed by the US Army for its multiprocessor systems, which, as most US Army project, has gone open source and has been ported to the, so a board support package has been ported to an NDS by a team of French students as their master course, computer science course project. So this is very impressive. These people have taken RTEMS, used the ARM9 cross-compiler, this is well known, but they have added all the initialization step and loading your RTEMS operating system into the NDS. It will give you most functionalities that I'm looking for from a Linux point of view. It will give you a TCP/IP stack. It will give you the feeling of a multitasking operating system, so it will run through multiple tasks. But it will also lack a few of these functionalities, and this is why it's called an executive environment and not an operating system. It will not allow you in its basic form, there are extensions that allow you to do it, but in its basic form it will not allow you to dynamically link libraries or to dynamically load programs. It's all static. An embedded executive environment will generate a monolithic application which includes all the applications that you want to run. You cannot dynamically add functions. It's supposed to be real-time. We will quickly discuss. Real-time is not my objective, so I will very quickly discuss this thing. But most important, in my opinion, is that it's got a very strong support. I mean, as opposed to all this collection of operating systems that you find on the web, I'm not claiming that it's not good to have a multiplicity of operating systems, quite on the opposite. But just as an engineer who has to choose a piece of software, and this investment, the 6-month investment that I'm taking, has to last long enough for this investment to be rewarded. And RTEMS is a US Army project. It's used now by the European Space Agency on a multitude of space missions. So chances are that in the next 10 years, it will not disappear from the web. And that's very important to me, the long-term support of wherever I'm investing time in learning. So again, in RTEMS, we'll do the same thing. We will first start with a Hello World project, so simply displaying something on the screen. Then we will learn to use the frame buffer. So again, we want to display things, so we want to access the display. And finally, I will show you how to acquire data. And since we have saved so much memory, we will be able to run the wireless data transfer through the Wi-Fi link. Now, RTEMS provides a Posix interface, a Posix compatibility interface, which means that a Posix programmer, or in other words, a Linux programmer, will find the environment very easy to use. Basically, this is an RTEMS program. You start with including a few of your files, including a standard input-output, standard library, a few dedicated NDS programs. You will start your program with, actually that's not the Posix compatibility. Here we are starting with init. You will see later you can start in the Posix compatibility mode with main. So you have a program that looks very similar to what you're familiar with. And the originality, the thing that at first looks unfamiliar on an RTEMS program is all these defined functions, at the end of a program. In an RTEMS program, let me remind you that you are creating one monolithic application that will run on your hardware, and this is very tight on constraints. So what you will do here is define all the peripherals that will be needed, no more, no less than what is needed. So instead of using, like Linux, all the available resources, here you will say, I just need that many devices, that many tasks, that many timers, and you will just define the resources that you need. So that's a little bit unusual for someone running a piece of software familiar with operating systems. But on the other hand, you have this Posix compatibility layer, which means that your program that you used to run on Linux will, of course, not run on RTEMS, but are very easy to port. For example, the people who have ported the board support package, the students who have ported the board support package, they have implemented the frame buffer. And the frame buffer means that exactly like you used to do on Linux, you will open your device, you will input-output control the properties of your device, you will memory map whatever address space your screen is located in, and again, you will write on the screen using assignment like we did before on Linux. So we have exactly the same kind of program structure under RTEMS than we had under DS Linux, except that you have a few initialization steps additional, which are dedicated to hardware initialization. So as an example here, this is drawing a fractal on the RTEMS, under RTEMS on the NDS screen, which shows quite a few things. This shows that we can access the frame buffer, but it also shows that floating point emulation is operating, and if you're familiar with this fractal calculation, it's calculating root solutions of polynomials. This means that you can actually perform pretty reasonable computations on an NDS. This is actually a little bit more than 48,000 polynomial root, third-order polynomial root calculations, which is performed in something like 10 seconds. Now, again, I want to access hardware, and this is usually done by writing to this address space, as we did exactly before under Linux. And if you do this, you have a bad surprise because it doesn't work. The bad surprise comes from the fact that this bus, I mentioned to you that it's a Game Boy Advance compatibility bus, which means that it's the ARM7 which is working on this bus. And DS Linux was assigning the bus automatically to the ARM